Math 265A, Cuesta College. I'm Joe Vasta, and we are going to be covering section 2.3, Techniques for Computing Limits. So in the last section, we actually looked at graphs, and we figured out what limits mean. We saw what this meant. It meant that two bugs are walking along the graph, and the limit asks for the y value where they're going to meet, and sometimes it doesn't exist. So let's take a look at computing limits without the pictures. And in your book on page 72 or somewhere there, they give all these limit rules here. So I'm going to show you all of them so you can see them. But it really doesn't have to be this complicated. They're pretty obvious. Like, you take the limit of a sum, then it's the sum of the limits. And you take the limit of a difference, it's a difference of the limits. It's almost like when you look at the sum, it's almost like this limit gets distributed in there, you know, like if you're thinking algebra. The limit of a constant times a function is the constant times the limit of that function. The limit of a product is the product of the limits. The limit of a quotient is the quotient of the limits. And this is provided that the limit of g is not equal to 0. Here's power and roots. The limit of a function to a power is, you could take the limit of that function and take that to the power. And the same thing with the root. This is the nth root. And you can do the same thing provided that f is greater than 0 for x near a when n is even, because you have some problems with square roots, fourth roots, and things like that. You don't want to take the square root of a negative number and start dealing with complex numbers. Now, after looking at that, you know, I would feel anxious if I was a student, like, oh man, look at all these limit rules. Really, we're not going to go there too much, because many of the problems that you will see in your homework in 2.3, where they ask you to find the limit, can be done using direct substitution. Now, what do we mean by that? Well, this is what I'm always going to try first off the bat, is putting 4 in for x and seeing what happens. So when I do that, I end up getting 4 squared minus 2 times 4 plus 5. So this gives me 16 minus 8 plus 5. And that's going to give me 13. Sure, we can graph this parabola, and we could investigate what happens at x equals 4 on that parabola, but it's going to be nice, smooth, and continuous. And I know those are some words that we still have to define, but it's going to be nice there. There's not going to be any holes or weird things. And you'll find that the y value is 13 and the bugs will meet. So that's how you do most of your limit problems. I would actually call this substitution. Now, can we use the other limit rules and say, hey, there's a power, and do all that stuff? Yes, we can. But if you're just computing limits without going over those rules and being rigorous, this is how easy it is. So let's try another one. Problem number 2. Maybe you want to pause the video and see if you can do problem number 2, and we'll see what happens. So the function on problem number 2 is 33. It's y equals 33, or f of x equals 33, however you want to say it, and you're supposed to plug 8 into that function. Well, the output of that function is always 33. Whatever you put into that, the output is always 33. So when I put 8 in there, the answer is 33. And so this one also happens to be substitution. Substitution means you just put 8 in for x. There was no x. So if this is making you feel a little alarmed or crazy, let's just think about what this is with the picture. So we're done with the problem. You have the picture of this. This 33 is a function, and maybe it's, well, it's going to be a horizontal line. Maybe it's right up here. And it looks like this. And here's 8 on the x-axis. And because the bugs are too big for this, I'm asking the question, will the bugs meet as they're walking closer and closer to each other? And the answer is yes, they're going to meet. And where are they going to meet? They're going to meet at the y value of 33. So everything we were doing in the last section is still true with this section, except we're learning how to compute limits without always having to draw a picture, because sometimes the pictures are not as simple as a line or a parabola, as you'll see in the next few problems. Let's go ahead and do problem number 3. So here is problem number 3. 4 is on there as well. And I'm going to see maybe if you can do these problems on your own. Pause the video and see if you can tell me what those limits are. Okay, so for problem number 3, I'm going to go ahead and plug 0 in. Now look, the letter can be different than x. So here it's H and over here it's T. So in your homework sometimes they'll put different letters in there. The most common letter is X when you're looking at calculus books. I'm going to put h equals 0 in there and see what happens. So I'm doing a substitution. I have 2 over the square root of 9 plus 5 times 0 plus 7. So this is 2 over the square root of, well, this right here, 9 plus 5 times 0, order of operations, say you do the multiplication, so it's 9 plus 0, which is square root of 9. And then we have plus 7 out there. And now I'm going to write this as 2 over 3 plus 7. So this looks like 2 over 10. Which we should always reduce our answer. This is 1/5. And that's how you do problem number 3. Problem number 3 was done using substitution. You might be wondering to yourself, like, are we going to do a problem where Joe doesn't write sub there, but there's something else? Yes, absolutely. Another question you might ask is, hey, when I see the word sub, I think sub sandwiches, I'm getting hungry. Well, if that's the case, pause the video, get a snack, and then come back. Let's go ahead and do problem number 4. Maybe you've already done number 4. I'm going to go ahead and substitute the -4 in for t in this function right here. So I have -4 plus 2 on the top. And on the bottom I have, look, -4 minus 4. So on the top I have -2, and on the bottom I have -8. 2 negatives make a positive when you're dividing, and you have 2 over 8, which is 1/4. Now, is it true that we can put the graph of this up and investigate the bugs walking toward each other toward the x value or the t value of -4? Yeah, but we don't really need to do that to do these problems, and that's the new thing of section 2.3. So this was done using substitution. So I'll just say sub. So let's go ahead and continue. This is all we are doing in this section. We are just investigating limits. Now, why are we doing limits? Because limits are going to help us grab on to instantaneous velocity. And more generally, they will help us grab on to rate of change. And that's going to be the whole heart of the first part of calculus when we learn something called derivatives. Find the limit of this function as x approaches 2. So let's go put 2 in for x on this. What I end up getting is 4 minus 2 minus 2 all over 2 minus 2. This gives me 0 over 0. Okay, so this one, when we try to do substitution in here, we got something that's bad, 0 over 0. So what do we do about this? Well, this will happen in your homework. And when this happens, you want to take a look at your algebraic expression here, this function, and see if there's some way you can do some algebra on here and maybe simplify it. So that's what I'm going to do. I notice that the top factors into, let's see, x minus 2, x plus 1. Okay, and the bottom is an x minus 2. So notice what happens here is those factors cancel, and I end up having the limit of just x plus 1 as x approaches 2. So now at this point, I'm going to try putting the 2 into this function and seeing what I end up getting, and I end up getting 2 plus 1. 2 plus 1 is 3. So how could I end up first having 0 over 0, and then I did some algebra, and then I ended up getting 3? We're going to classify these problems as reduced. Why did this happen? Let's get a little bit more into this. You might have remembered from pre-calculus that when you cancel with a rational function, a polynomial over a polynomial, and you get some canceling, what that does is that puts a hole in the graph. So, like if you're thinking of this right here, what happened is there is a hole at the x value that got canceled, which the thing that made that undefined was 2, hole at x equals 2. Now the y value of the hole, so the hole is actually going to be a point here. You'd put the 2 into the function and you end up getting 3. So that's the limit. So let's go ahead and graph this. We're done with this problem, but I'm going to show you the graph because some of you are picture people. We have our x-axis and our y-axis. 1, 2, 3, and then we over here's 1, 2, 3. We have -1 here. What I'm going to do is I'm actually going to graph this function here. Now this function is really the graph of x plus 1 with a hole at 2, 3. Well, x plus 1 has a y-intercept of 1 and a slope of 1, so it looks like this. Got a little smearing here. And at, whoops, try to get this good, at 2, 3, 3 is a little up there. There's a hole in the graph. Okay, it's not perfect. If I had used grids, it would have been a little more perfect. See, the scaling's a little different. This is the 0.23. And there's a hole in the graph. So what does this tell us about the limits? Well, the limit as x approaches 2 on this function. So you're approaching 2. You got 2 bugs. That's what the limit is. Are those 2 bugs going to meet right before they step off onto x equals 2? And the answer is yes. They're about to meet at the y value of 3. And so when you cancel, you'll end up getting a hole in the graph. Now, we'll get some other ones, and you might think, well, can I just do the graph and do it based on the graph? Well, the graphs of some of the future ones that you get will be a lot more complicated to draw, and that's why it's best to know the algebra. Okay, so we will do that then. We'll do more problems where we end up getting 0 over 0 when we do a substitution, and then we'll end up doing some algebra, some counseling, and find out what the limit is, and there's a hole in the graph. Once again, some of you are like, wow, I've got a friend in another calculus class, and they do Zoom sessions, or they're doing PowerPoint, whatever. There could still be time to switch. You can pretty much go to almost seems like you can go to any college you want to go, any community college. So if you don't like this, there's still time to run. But this is what I do. I'm going to write on a piece of paper. I know creating PowerPoints takes a lot more time, and it's not as natural. At least when I'm writing, you can kind of see maybe what you can do when you're doing your homework. With PowerPoints, sometimes things just get put up there really quickly, and it's not as natural. This is not to say we won't see some PowerPoints in this class. I may do some PowerPoints for some derivations, but not for working out the problems. I'm going to put 0 in there, and you can already see, look what happens on the bottom. There's a 0 there. So let me go ahead and, in red, I already know something's wrong with this. 0's on the bottom. And then on the top, we end up putting 0 in for x, and we get 0 on the top. Now, just like the last one we got -2 over 0, and this one we have 0 over 0. Sometimes when 0 is on the bottom, you are in trouble, and the limit doesn't exist, or we have infinity and negative infinity. So we'll have that discussion in a later section. But right now, let's see if we can do some algebra to this expression here, and see if anything will reduce. Okay, so my next step is to write the limit as x approaches 0. And the only algebra I can think of is to multiply out that top. Okay, I'm not going to try to factor that top because there's parentheses and all that stuff. I'm just going to simplify that top by multiplying that out and subtracting 9. Now, over off to the side, maybe in purple, we just got to remember that when you have this, and it's so tempting to do, that we do not want to write 9 plus x squared. What this is 3 plus x. Quantity squared is 3 plus x times 3 plus x. So we end up getting 9 plus 3x, which is plus 6x. And then this is plus x squared. Okay, so this is, why don't I just make a cloud off to the side? You might be saying, wow, that's a pretty cool cloud. That's the only good thing that I can draw. Okay, so I don't teach art class because the other things that I draw don't look good. I'm going to go ahead and replace that 3 plus x quantity squared with what we have here, those 3 terms, 9 plus 6x plus x squared minus 9. This is all over x. So what do we notice on the top that we can do now? Well, we can cancel those 9s, and so we'll get rid of them. We'll write out that next step here. This is the limit as x approaches 0 of this function here, which is 6x plus x squared all over x. Now what can I do? Well, this is kind of like the other problem where on the top we can now factor it, and we can factor an x out of the top. So that's what I'm going to do. The limit as x approaches 0, factor an x out of the top. So I have 6 plus x. On the bottom I have an x. Okay. Don't you hate when you go to cancel an x and you cancel by crossing things out? And then you do that, and then you look and you're like, whoa, what happened? Oh, let's cancel them again. That can get frustrating. That's why I take out this red pen. So just get rid of that completely. So, like, you know, so you're saying, was he trying to tell a joke or something? So this is what I mean. Go to another class. If you're just sitting there going, man, that was so pathetic. I'm doing that because there are actually people who want to get into this class. Sure, they don't know what they're getting into, but if we can clear out some of the people who really hate my style, that would be a good thing. Okay, the x's cancel, just like the x minus 2's canceled in the last problem. So let's rewrite this. So basically what we did is there's a hole in the graph. There's a hole in a graph. We don't even care about that anymore because it's not really going to help us get our answer. The limit as x approaches 0 of this function here. So all I have to do is do a substitution, replace the x with a 0, and I end up getting 6 for the answer. There we have it. And so I would say that this one was also a reduce before we sub, just like the last one. So that is the answer. We're going to go ahead and do more of these. This can get a little dull in terms of just watching the video. I'd also have to say that there are some things missing by taking an online class, or a remote learning class is a better description. The things that are missing, just think about when I was a student. The things that are missing are the interaction with the teacher, eye contact, you can ask a question, etc. And the other thing that's missing, at least when I went to college, is there's other students. There's people your age. You guys are all in the same room, and you meet people and you interact, and it's more exciting than taking remote learning. So if you're sitting there and you're doing remote learning and it's not as exciting, or you feel that it's really dull, you're not an outlier. I mean, that is what a lot of people are thinking right now. So just hang in there. I really don't know what to say. I can solve this problem here, but I cannot solve the problems of viruses and governments telling us what we can do, what we can't do, etc. It's very complicated. And so sometimes when you think of the world, if you turn on the news, you're just saddened. And maybe this class and watching these videos in some sick way is a little bit of escapism from that. And not only do you get escapism, but if you have to take calculus, maybe it's a good deal to do that. Let's go ahead and maybe I should cut that part out. Nah, let's just keep it in there. It's too much work. Okay, I'm going to put 1 into this function, 1 in for x. And so on the top I'm going to get 2 plus 1 on the bottom, so I'm going to get like 1/3 minus 1/3, which is a 0 on the top. And on the bottom, put 1 in there, I get 0 on the bottom. So maybe you can pause the video and see if you can figure out how to do this. Is there any algebra that you can do? Can you simplify this complex fraction, or some teachers call it a compound fraction, just because there's fractions within fractions. So if you ever remember doing that, pause the video, do it, and then if something cancels, see if you can get an answer. Okay, so what I'm going to do now is I keep losing my rulers and I have to go find these new rulers. I don't know what's happening. Okay, so I draw a line, and what I'm going to do is I'm going to go ahead and put this expression here, 1 over 2x squared plus x, and then we have minus 1/3. This is all over x minus 1. I'm going to get a common denominator on the top. Okay, So some of you might go, oh, well, you can factor an x out of there. And so, you know what, I'll do that. I'll humor you. Because sometimes if you factor something out of there, it shares a factor with the other denominator. And so I'm going to factor an x out. And I have 2x plus 1. Okay. And then we have minus, leave some space, 1/3. This is all over x minus 1. Okay, so now I'm going to get a common denominator. I'm going to ignore the bottom here, this x minus 1. I'm just going to put those together, and I'm going to get a common denominator, and it's going to be 3 times x times 2x plus 1. So this guy right here needs a 3. Now we can't just go around putting 3's on the bottom of fractions. You've got to balance the books by putting a 3 up there, but put a dot there so it doesn't look like 31. Now over here, this guy's looking at his neighbor and he's all, man, I want all that stuff. And you have to build them up to get that denominator. So he needs an x and an x, and he also needs 2x plus 1. So we put a 2x plus 1 on the top. Okay, so what I'm doing is I'm not writing the limit every time because that's just going to be a pain. I'm just doing some algebra on this. So I have 3 minus that on the top. 3 minus x, 2x plus 1. And then we have this is all over 3x, 2x plus 1. This is all over x minus 1. So you might be wondering, can I just cancel the 2x plus 1s? That's what a lot of people do, but it's incorrect. In order to cancel, you have to have one term on the top and one term on the bottom. So let's just let's put a piece of paper over this right here. Let's just ignore that. And you don't have one term on the top. You have two terms, the 3 and then this thing right here. So no canceling when you have two terms on the top and one term on the bottom. So you just have to multiply out the top and see what you get. Okay, I mean, when I say multiply out the top, simplify it, distribute the negative x. So I have 3 minus 2x squared minus x, and then this is all over 3x, 2x plus 1. This is all over x minus 1. Okay, so we need another piece of paper. So there we are right here. Hopefully we're being efficient here with the paper. And so this is going to equal, well, I don't know, let's see. I think it's time for a copy dot flip. I'm going to put this over 1, and I'm going to go ahead and write this first fraction, that's the copy. This big division becomes a dot, and then we're going to flip that. So copy, dot, and then flip. Okay, so it looks like I'm doing lots of algebra. Maybe there will be some canceling, maybe there won't. The next thing I'm going to do is try to arrange these so the x squared is first. So negative 2x squared minus x plus 3 on the top, and on the bottom I have 3x, 2x plus 1, x minus 1. Okay, so I'm going to see if I can factor that trinomial. And I don't like to factor trinomials when there's a negative in front. So I'm going to factor a negative 1 out front. This is going to give me a 2x squared plus an x and then minus a 3. This is all over 3x, 2x plus 1, x minus 1. Now we can try to factor this. This is a trinomial, and you can do your factoring of trinomials. Hopefully this one's not too bad because it's just a 2 and a 3. It's still kind of bad. 2x and x, and perhaps a 3 and a 1, and so this gives us a 3x and a 2x. So yeah, we have a plus there and a minus there. So we have 3x minus 2x is x minus 3. Okay, I'm just double checking. And then on the bottom we have 3x. We have 2x plus 1, and then x minus 1. So what happens here, we can cancel the x minus 1s. Wow, all that work for that. And so now we're going to go back to our original problem. See if I can make a line again going across this paper. That's what I'll do. And the original problem was limit as x approaches 1 of this mess right here. It's a pain to write. X minus 1. Remember, we plugged 1 in there at the beginning of the problem. We found 1/3 minus 1/3. We had 0 on the top and 0 on the bottom. But now we were able to do lots of algebra on this. Cancel the x minus 1s, and I have the limit as x approaches 1 of this new thing right here. So negative 2x plus 3 on the top. You don't actually have to write the 1 there. And then we have 3x, 2x plus 1. Let's go ahead and do a substitution, putting 1 in for x. So I don't have to write the limit now, and I have negative. Putting 1 in for x, I have 2 plus 3 there. I'll write this out. And on the bottom, I have 3 times 1, and then we have 2 plus 1. So on the top, we have negative 5, and on the bottom, we have 3 times 3. So it looks like my final answer is negative 5/9. That was quite a problem. What I do is I try to take problems that look like the homework problems. So that way when you do the homework problems, you'll go, oh yeah, we've seen some of those in lecture. So number 7 was quite bad. And what was the worst part about number 7? The worst part about number 7 was the algebra. I'm going to say on this one was a reduce. In fact, some of you by the end of this semester will say the worst part of calculus was algebra and trig. And the calculus was actually pretty interesting. Some of you may say that. Okay, problem number 8. We have this right here, and then the first thing I always do is plug the 4 in. So what's the square root of 4? Square root of 4 is 2. 2 minus 2 is 0. And on the bottom I have 4 minus 4, which is 0. Okay, so usually we try to reduce this, but now it seems like, how can I reduce this? So that's the question. I'm going to do some other kind of algebra, and we'll draw a line because we're going to focus on the function and see what we can do with that. And some of you might already have an idea what to do. So we have square root of x minus 2 on the top, and then 4 minus x on the bottom. What I'm going to do is I'm going to put parentheses around both of those, and this radical, it's like says root x minus 2 is in the numerator. And you may have remembered something in an algebra class about rationalizing the denominator, getting the radical out of the denominator. Well, ours is in the numerator, and so what I'm going to do is I'm going to rationalize the numerator, which means I'm going to write square root of x plus a 2 on the top. Okay. Now, we can't just take an algebraic expression and multiply it by root x plus 2. Whatever we do on the top, we should multiply it on the bottom as well. Okay, so on the top, when you FOIL this out, you get, the reason I chose the plus instead of just doing the same thing is the the inside and the outside term are going to cancel. Look at this. I'll write it all out this time. Root x times root x is x first. Outside is going to be 2 root x. Inside is going to be minus 2 root x. And last is going to be minus 4. And on the bottom we just have 4 minus x times this. I'm not going to FOIL that out because it's going to make quite a mess. So on the top, those guys are out of there. And notice what you get on the top. You end up getting an x minus 4. And on the bottom, you have a 4 minus x factor. Okay, and there's also this factor here. Now notice the 4 minus x and the x minus 4, they are opposites. So I'm going to factor a negative 1 out of the top. And I have a negative x plus 4. 4 minus x, root x plus 2. And some of you are ready to just cancel, but I'm going to rearrange those terms. So I'm not doing any factoring. I'm just rearranging it. So I'm going to write 4 minus x on the top times that negative 1. And then we have 4 minus x on the bottom. Then we have root x plus 2. So look what's happening. Those cancel. And my algebraic expression becomes negative 1 over root x plus 2. So I've rationalized the numerator. I got rid of the radical in the numerator. Now it's in the denominator. There's a radical in the denominator, but oh well, let's go ahead and try this out instead of that one. So go ahead and put a line here because now we're done doing the algebra. And this limit as x approaches 4 of, I'll just write out the problem again, 4 minus x. This equals the limit as x approaches 4 of negative 1 over root x plus 2. So now I'm going to do substitution on this one, putting a 4 in for x. And what is the square root of 4? The square root of 4 is 2, and we have 2 plus 2 on the bottom. So our final answer is going to be negative 1 over 4. And so yes, we did reduce, but because this had radicals and we had to rationalize something, what I'm going to call this is radical. I'll just say rad. And that's what we did. We'll do another problem that has a radical, and that messes up where there's a 0 on the bottom of the fraction, and we'll see how we do with that. So number 9. Okay, maybe it's a good time for you to pause the video and see if you can do this one on your own. Okay, so I always try plugging 0 in first because you never know when they sneak a problem in there that could just be done really quickly. I get 0 on the top, and that actually doesn't concern me that much. I mean, what if I had 0 on the top and this was a minus 7 down there and I ended up getting like a negative 6 on the bottom? And that would be 0 over negative 6, which is just 0. It's when I get the 0 on the bottom that really just gets me. So put 0 in there and we get root 1, which is 1, 1 minus 1, which is 0. So yeah, that's not happy news there. It just means I have to do some algebra. So I'm going to go ahead and draw a line, and we're going to do some algebra on this one right here. So this is x all over root 1 plus x minus 1. So now the radical in the last problem was in the numerator or on the top, and now the radical's on the bottom. So why don't we go ahead and rationalize the denominator and try to get rid of that radical on the bottom. What I'm going to multiply top and bottom by is sometimes called the conjugate, I didn't use that word last time, but that's what we'll do right here. So it's going to be whatever that square root is, root 1 plus x. We're not going to go minus 1, we're going to go plus 1. Now, if there was a plus 1 down there on the original problem, then we'd say minus 1 over there. And so on the top, I'm going to multiply the top by the same thing. It's like multiplying a fraction by 7 over 7. You're not changing the value of that. Sometimes when I'm grading tests, I'll see someone do the bottom correctly and then they'll put a minus on the top. But we don't want to do that. We want this to be the same because we're multiplying this fraction really by 1. Okay, the reason we picked this conjugate is because of what's going to happen on the bottom. So the top looks like this, x times root 1 plus x plus 1. And that's in parentheses. On the bottom, when we do the FOIL, we do first, which is going to be root 1 plus x times root 1 plus x. It just gives you a 1 plus x. Outside and inside, you can check this out for yourself, they will cancel. And so the only other thing I'm going to write on the bottom is minus 1. Okay. Now, look at the bottom. Look what we can do on the bottom. We can get rid of the 1 and the minus 1, and you just have an x. So it looks like this. X times the square root of 1 plus x plus 1. This is all over x. So, looks like we can cancel the x's. And you just have this root 1 plus x, and then plus 1. So let's go ahead and draw our line, and then get back to what we're doing here. So this is the limit as x approaches 0. So this is the original problem. And so we went ahead and manipulated it using algebra, that expression. So we're going to say limit as x approaches 0 of square root 1 plus x plus 1. So now when we put 0 in for x, we get root 1 plus 0. So it's root 1, which is 1. 1 plus 1 gives me 2. 2 is the limit. And that's how you play the game. This one we'll classify as radical. But really with the radical we reduced. And when you cancel, it does put a hole in the graph. So there is a hole involved, and two bugs are walking toward the same hole. They are still going to meet at the y value of 2. But because this thing looks so funky, we really don't want to graph this one. We didn't want to graph the other one from problem 8 as well. Let's go ahead and do number 10. Number 10 involves some trigonometry. Let's see if we can do this. So when I put pi in for x, you've got to remember what the cosine of pi is. Now I know some of you might say, well, I can always just take out a calculator. I'm going to be a purist here, and I'm going to say I just remember the cosine looks like this, and it goes for a cycle 2 pi, and then here's pi. So it looks like the cosine of pi is going to be -1. So I'm going to go ahead and substitute the pi in for the x. I have 3 times pi times the cosine of pi. 3 pi, and the cosine of pi, like we said, is -1. And so this graph right here that I drew is not 3x times the cosine of x. This is just the simple graph of y equals cosine x, because then it helps me recall what this cosine pi is. So I end up getting -3 pi for the answer, and this right here was just a substitution. But it had some trig in it, and that's why I did it. In case you get a few problems with trig in it, just be prepared psychologically for that. Okay. We're getting pretty high in our numbering system. We're on number 10, so I'm going to start it back at number 1 again, and the next 7 problems are going to involve the same function. So here goes. Let f be this piecewise defined function. Okay, so hopefully you've seen these before. Another name for piecewise defined function, sometimes you might hear me say this. This is also called a branch function. Okay. Now, this branch function, you know, this 4 and this x squared and the x plus 1, they look pretty nice, and there's sometimes when this function goes from the top road to the middle road and from the middle road to the bottom road. So we got to be aware of those values of x's where that happens. X equals -2 and x equals 0. But right over here, number 1 says the limit as x approaches 7 of this function. Really what we want to do is we want to put 7 into the function. So you have to know how to feed this function. And to feed this function a 7, 7 is not less than -2 and it's not between -2 and 0, it's greater than 0. So when you feed this function 7, you know, so if you went f of 7, you would actually put it down here. So you would go 7 plus 1, which is 8. So there's no problem with doing a substitution on this. This one's just a sub, and you get 8 for the answer. The only 2 problem points on this problem would be -2 and 0, because those are where things change. So now, let's go ahead and look at this. Oh, before we move on, some of you are like, but Joe, we did one of these last time and then we had to graph it, and then we just used the graph to analyze these limits. I am intentionally doing this without a picture because that's what you want to do. If you get one of these, you don't always want to draw the picture. So when we are taking a look at -2, look, this is the limit of f as x approaches -2 from the left. This is the limit of f as x approaches -2 from the right, and then if these guys give you the same number, then this one's going to exist and be that number. Okay? And if not, then this one's going to be DNE. So what we're really focusing here on is this right here. We're focusing on -2 for the next 3 problems. And -2 is right here. Now, which one is on the left? Well, it would be when x is less than -2. So I'm going to say this is left. And then this one here is right. Okay. In fact, if you end up feeding this function -2, it's actually going to be fed down there. Okay. So let's see what happens as you approach -2 from the left. That means you're going to be putting -2 into that function. And that's just a constant function. So if you put -2 into that thing that says y equals 4, it gives you it gives you just a 4. So you put -2 into that constant that says 4, it's just 4. And that's coming from the left. So basically, you know, if you're kind of looking at this later on, I just plugged -2 in the top road. Now when I come from the right, and that's what that little plus means, then I'm looking at the function that you plug it in when it's on the right. And so what are we going to do here? I'm going to put -2 down there. So this is going to be -2 quantity squared, which gives me 4. So that's pretty cool that this one's 4 and this one's 4. It means that when you jumped from that one, from the top road to the middle road, you didn't jump at all. You landed exactly where this one left off. And so, the limit of f as x approaches -2 from both sides, well, you can then, with confidence, say that it is 4. Whereas if this said 4 and this said like 8, then you would say DNE for that one. So the next 3 problems I'm going to go ahead and approach 0. And in fact, might be a good time for you to pause the video and get a snack. No, pause the video and see if you can figure out what these are. Okay, so now what I'm going to do, I'll use a different color here. I'll use green. I'm investigating 0, 0, 0. So here's where 0 is. And then the one up here from -2 to 0 is on the left. What is that? Look at that. So you can see the pen's falling apart. This is what happens when you get your stuff at the dollar store sometimes. And then this is the right part of it. So this is right of 0, this is left of 0. I mean, 0 is actually included on that one when you're evaluating the function. So the first one says limit of f as x approaches 0 from the left. From the left, so you just put 0 in there. This is going to be 0 squared. So I'm putting it right there. 0 squared is 0. So this one-sided limit does exist. It is 0, and we approach things from the left there. And over here, because there's a plus there, that's approaching 0 from the right. And the right would be the bottom road here. So this would be 0 plus 1. Let's write that in there. So I'm still just plugging 0. I'm just plugging it in. 0 plus 1, and that equals 1. Okay. Now look, the left-hand limit and the right-hand limit do not equal. So what are we going to say about the limit of f as x approaches 0? We're going to say this does not exist. DNE. And that happens. And if you were to graph this graph, you'd be traveling on the parabola, and then you would hit right at 0. You'd be right on 0, 0, and then immediately you would jump up to this line, x plus 1. And so you'd be right at 1. And so you would see that those two graphs do not touch each other, and the bugs would not meet, and that's why it says DNE. So that completes a lot of these kinds of problems. There's one other topic we want to cover in section 2.3, and it has the name of the Squeeze Theorem. Some books will call it the Pinching Theorem, and some books will call it the Sandwich Theorem. I'm sure there's probably other names. And so this is what we have here. We are evaluating this limit, this function, as x approaches 0. And when I put 0 in, this part gives me 0 squared, which is 0. I'll just write that out. Times, when I go ahead and put 0 over here, I have 1 over 0, and I'm taking the sign of that. This is a DNE. This is a 0 times a DNE. So we're really stuck with something like this. I can't do any algebra or anything. So at this point, we wouldn't know how to do this limit without learning about something called the Squeeze Theorem. Okay, what do you know about the sign of a function? Y equals, let's just say sine x. Well, the sine x looks like this, but it oscillates between what two values? Between 1 and -1. Okay, the sine of 1 over x, I'm not going to draw it, but it's also going to oscillate between -1 and 1. Okay, because you're still taking the sign of different arguments that are real numbers. They're never going to be outside the -1 to 1 range. So I'm going to write that down. The sign, I'm going to write it down in a mathy way. Sine of 1 over x depends, we'll just do it this way, is squeezed in between 1 and -1. So we'll start off by doing that. At any moment this camera is going to shut off. I don't know what the deal with that is. Well, anyway, we'll just continue. Okay, so now what I'm going to do is I'm going to multiply all three parts of this inequality by, I'm looking at this is what I need, by x squared. So when I do that I get negative x squared less than or equal to x squared sine 1 over x is less than or equal to 1 times x squared, which is x squared. Okay, now I can get away with that because x squared is a non-negative number. When you multiply inequalities with negative numbers, the inequalities flip. But because x squared is non-negative, that means it could be positive or 0. It's not going to flip those inequalities. Now here's the whole tricky part of this. You have these three parts. I'm going to say the limit as x approaches 0 of negative x squared is less than or equal to the limit as x approaches 0 x squared sine 1 over x less than or equal to the limit x approaches 0 of x squared. I'll put parentheses around that. Okay, so the camera did stop. So I'm picking up where we stopped it. So this is the whole part of the squeeze theorem. Do we know the limit of negative x squared as x approaches 0? We could just do a substitution and we end up getting, for this one, let's just say this guy right here goes to 0. And the limit on this one right here, limit of x squared as x goes to 0, you go 0 squared, so this one goes to 0. And notice, look, you have both sides, both pieces of bread. Think of this as a sandwich. No one would really like to eat that kind of sandwich, but both pieces of bread are going to 0. So what do you think the middle one's going to do? The middle one's squeezed in between those functions, so it will go to 0 as well. So, by the squeeze theorem, I'll abbreviate theorem, we can see that the limit as x approaches 0 of x squared sine 1 over x has to equal 0. And 0 is the answer. Now the squeeze theorem cannot always be applied to every situation, but there are some functions where you can't seem to get the limit in, and if you do the squeeze theorem, you can. So here is some pictures that may satisfy you. This is the picture of x squared sine 1 over x. So let me write that up. This is y equals x squared sine 1 over x. Now you've got to be careful when things wiggle, because, well, what I'm trying to say is you can't always go by the picture. Sometimes, it looks like the limit is going to 0, but you should never just go by the picture, because we can come up with a funky example where it looks this way, but it's oscillating between -1 and 1 and the limit doesn't exist. So cannot always go by the picture, but that's the picture of the one that we're doing. We're taking the limit as x approaches 0. So what the squeeze theorem did is it says that function squeezed between those two parabolas. And since we know the limit as x approaches 0 of the top parabola and of the bottom parabola, and those are both 0, this function that's squeezed in between those parabolas, its limit at 0 must be the limit of the other guys, which was 0. So this concludes this section, which is section 2.3. Do your homework. Our next section is 2.4.